stage for the last talk of this session. And Fabio is already on the stage. So Fabio is going to present a joint work with Enrico Pontelli, and the title is Parallel Declarative Solutions of Sequencing Problems Using Multivalued Decision Diagrams and GPUs. Okay, Fabio, stage is yours. We have 20 minutes.
Okay. Can you hear me?
Yes, perfectly, and you also see your screen and your mouse pointer.
Perfect. So, hello everyone. My name is Fabio Tardivo. I come from New Mexico State University, and today we'll talk you about parallel declarative solution of sequencing problem using MDD and GPU. The overview is this. I give you a really light introduction about the topic and the context, an introduction on multi-value decision diagram. I will talk about large number search. I will talk about what we did, and in the end, some result and conclusions. So the problem is this. Recent application involving sequencing problems like routing operate almost in real time. And these requires to solve such problems, such combinatorial problems, in a small bounded amount of time. What we propose is a method that quickly provides good solutions. And it makes use of three technologies that are multi-value decision diagram, the large neighbor search, and general purpose computing on GPU. Okay, a little bit information about the context. So what is a sequencing problem? A sequencing problem is a problem that consists to find the best order to perform a set of tasks. If you want the best permutation of the tasks. What is a multi-value decision diagram? So really oversimplified, a multi-value decision diagram, or MDD, is an encoding of the solution of a combinatorial problem as path in a direct acyclic graph. And why we should use MDDs for solve these problems? What are the benefits? The benefits are they enable the search to easily focus on the more promising part of the search space, and they can be constructed in parallel really easily and really quick. So an example of multi-value decision diagram, like take a constraint satisfaction problem. We have 4 variables over here, each one with in the domain of 0, 3. Subject to an all different constraint, and then x1 should be bigger than x3, x2 should be smaller than x4. So here we have the corresponding MDD. For each path from R to T correspond a solution, and for each solution there is a path. For example, the assignment x1 equal to 3, x2 equal to 0, x3 equal to 2, x1 x4 equal to 1 is a solution. So multi-value decision diagram can be seen as labeled transition system. And just to refresh what labeled transition system is basically a tuple as lambda and t, such that S is a set of states, lambda is a set of labels, and t is the transition function that given a state and a label return another state. The intuition here between the MDD and LTS is that a state on the labeled transition system represent a set of partial solutions, and a transition from state S to state S prime labeled with L basically extend some partial solution of S by assigning L to some of the unassigned variables. Okay, now how this labeled transition system is made. Let's consider a CSP with n variables and the corresponding MDD m. The labeled transition system is such that the set of states is partitioned in n+1 layers. The labels are all the values in all the domains of the problem, And the transition function connect two layers, LA and LA plus 1, with a value for the variable XA plus 1. And this is valid for all the layers. So for example, here, this layer basically assign the values for the variable XA plus 1, and the label on these edges, it will be in this set. So about the semantic, as we said before, as each state represent a non-empty set of partial solutions, and the state in a layer A basically partition the solution of length A, the partial solution, sorry, of length A, and then a transition from state S to state S prime labeled with L, from layer A to layer LA plus 1, extend the partial solution by this assignment. Okay, so multi-value decision diagram are really powerful, but they grow really fast in the numbers of variable. They can grow exponential. So what is common practice is to bound their width. These allow a trade-off between memory and time to build such structure, and this kind of MDD are called restrict MDD. So how we bound the width? We just discard some state. When there are too many states in a layer, we discard some state. Of course, we may lost solutions. And how we decide which state to discard? Basically, we rely on the cost function of the optimization problem. So we inspect each state and the partial solution in each state, and we pick the best one. And based on this value, we sort the state and discard the state with such that the best partial solution is worse. Okay, so the schema that I showed you before lead to a greedy approach, since we discard the states with the partial solution, with the worst partial solution. How we address the problem? We address this problem with large neighbor search. What is large neighbor search? Is a method, is a heuristic that's given an initial solution. It destroy part of it and repair part of it, so to find different solutions. Okay, that's could make sense, but you have to be lucky to find a good solution. You're transforming one solution to another one, but there is no guarantees that is better. That is true, and that's why we do many large neighbor search in parallel, both on CPU and GPU, and we don't use any problem-specific heuristic. We just destroy a random part of the solution. Okay, now to merge these ideas, we propose to use restrict MDD to repair the destroyed solution in the large neighbor search. So consider again the problem that we saw in the beginning. Now, for each solution, we can have its cost. That's basically given by this function. So yeah, this solution correspond a cost. Here, there is the complete table for the complete solution, for all the solution and their cost. Basically, if you read in this way the solution, the cost is the opposite. So it don't work well with the greedy approach. And here is how we, an example, how to repair the solution, the destroyed solution with an MDD. So suppose that we start with this one, with this solution. Since is one solution, there is an MDD with just one path. And we decide to destroy this assignment and this assignment. This lead to this MDD. We construct this MDD top-down. So we start from the root. We can choose the value 1, 2, 3, but since 1 is already fixed, we cannot. So we can choose 2 and 3. Then x2 and x3 are fixed. So the only outgoing edge here is 0, 0, and 1, 1. And then in the end here, the only possible complement is 3, and the only possible complement is 2. Here there are two solutions encoded, so 3102 and 2103. And so we can move from this solution, sorry, I read it in the opposite way. Here the solution are 2013 and 3012. So from this solution, now we have also this solution represented in this MDD, and so we can find another solution that have a better cost. How we perform the large neighbor search on our approach. So we launch the program. Initial solution will be greedily found on the CPU side. And then we launch many large neighbor search both on CPU and GPU. And when this search finished, one round of this search finished, so I have n copies of the solution. I destroy this copy in a different random way. I repair these copies and check for better solution. This is a round. When a round is finished, I check the timeout. If it's over, I will, and otherwise I will launch another round of large neighbor search. Okay, as I mentioned before, we do large neighbor search both on CPU and GPU. So how we do on CPU? On CPU, we use wide MDDs, wide restricted MDDs to consider less greedy choices. So for each assignment, I discard less and less state because I use a wide MDD. So what I'm looking in the neighborhood is I really explore the neighborhood less greedy as possible. And we do this by creating one MDD for each thread that we have. What we do on the GPU is complementary in the sense that we use many narrow MDDs to consider different choices. Why this? Because if you are in an unlucky neighborhood, if you free the variable that's for as good as you are looking, you cannot find a better solution. Maybe it's better try different neighborhoods. And also if you're looking at neighbors like lazily, you can find a better solution. That's why these complementary approaches. And here in the GPU, we create many MDDs in parallel, and each MDD is created in parallel itself. So there are many threads for each MDD. So as I tell you, there is this trade-off between the behavior of the CPU and the GPU, and the implementation allow you to tune these parameters, like the width of the MDD, the number of the MDD on the CPU, same for the GPU, and also how much is destroyed the solution in the large neighbor search. For example, I want this destroy just the 30%, the 50%, whatever. So now that we have a method, you can ask, what is the benefit of this approach versus backtracking? Why I don't repair the solution by backtracking? The main benefit are two. That's MDD enable a generic cost-driven heuristic. And the second benefit is that MDDs can be parallelized efficiently and also in the GPU because each transition is independent. And another question will be, how hard is model a problem using this approach? Not so hard. You need to provide four things: how you represent a state, the initial state, the transition function, and the cost function. Once you provide these approaches, everything will be managed by the implementation. So the MDD will be built by the implementation, the large neighbor search will be done by the implementation. Okay, to be more precise, we relaxed some constraint on the definition that I gave you before. This is what we find as the best trade-off. A state right now, we allow a state to represent, also, my fault, we require that the state represent only one partial solution instead of a set. And that's lead to the fact that we allow to have multiple copy of the same state, because when before we have one state with two outgoing edges, now we have two states, each one with one outgoing edge. And then we allow the transition function to be more flexible, in the sense that it can return state that represent assignments, partial assignment, that are not partial solution. What are the benefits of this trade-off? The benefits are the following: that we represent a state by a triple, where P, C, A, where P is a partial solution, C is its cost, and A is the set of the unmissable values for extending P. The another benefits is that the underlying structure is a tree, and the best solution is encoded in one of its leaf. And if you, it's possible to build this tree in a constant time, in a constant amount of memory, since we build top down and we consider the layer I and the layer A+1. We need just to take these two layers, so we have a sliding window pass through the MDDs during the construction. And finally, for what's concerned the transition function, you can inject how much knowledge about the problem that you have. You can make a function that return every time a state that represent partial solution, or just a function that's given a state and a value, tells you if there will be a valid state, and in such a case, it will create. Okay, an example of encoding is, I will pick a traveling salesman problem that is a classic combinatorial problem. So we have a set of cities, C1, Cn, and a distance function that given two cities, it returns the distance. And we want to find the shortest route that visits each city and return in the beginning. So the state, we can use the representation that I gave you before. So partial solution, cost, and unmissable values. The initial state is such that the partial solution is empty, the cost is 0, and the value, the unmissable value to extend this are all the city, of course. And the generic transition given a state and another state is such that, of course, you append the state, the city that you visit on the partial solution. You update the cost from the distance of the visited city from the one that you visit last, and you remove the city that you just visited from the set of the unmissable values. Of course, the first transition, the last transition are a special case, because you don't have a city where you come from, and you have to go to the initial city. Okay, we test our ideas in a bounded time application with a 60 seconds timeout on 3 problems. A sequential ordering problem that is a classic routing problem with precedence constraint. An open shop scheduling problem that is scheduling problem with a really, really big search space. And the cable tree wiring problem that is a scheduling problem with disjunctive constraints. We compare with 3 solvers: G-code, that is a state-of-the-art constraint solver; G-code LNS, that is an LNS implementation based on G-code; and YAC, that is a state-of-the-art local search constraint solver. This is the results for sequential ordering problem. So here we have the plot. This line represents the best known solution for the problems. and we compare these two metrics. That the average time is the average time took by the solvers to return the best solution that they found within the 60-second timeout, and the average gap, that is how much on average the solution are distant from the best no solution. Here we have that's MDD plus LNS is on average after 30 seconds return solution that are really close to the best no. YAC, that is good, but it tends to be, the solution is tending to be 2 times the cost of the best one. And then G-code and G-code LNS that are really far away in this benchmark. I have to mention that for some instances, both YAC, G-code, and G-code LNS was not able to return a solution within the timeout. For the OpenShop scheduling problem, we have a different situation. MDD plus LNS still have optimal good performance, but they are surpassed by G-code and G-code LNS, and YAC it's fall behind. Why we have G-code and G-code LNS performing so well in this case? That is why the constraint programming model used is really really optimized for such a problem. For the final benchmark, the Cabal 3 wiring problem, we have a more average situation where MDD plus LNS still give you a good solution in less than 30 seconds, and the other approach fall behind on solution of cost between 3 or 4 times the one given by MDD plus LNS. Again, in this benchmark, both G-code and YAC was not able to give a solution for some instances within the timeout. And finally, some observation, conclusion, and open questions. We can see that MDD plus LNS is consistently good among all the benchmarks. On average, the solution is just 50% more costly than the best known solution. That's consider that they are found in a 30-second timeout, in 60-second timeout, and on average on 30 seconds. It's a good result. And the open question is the following. We create a lot of solution and we explore a lot of search space by the large neighbor search. Can we learn from something? Can we learn something from that? And the next question is, if we can learn something, can we guide the search with the stuff that we learn? And that's it.
Okay, thank you very much. It's a little bit more than the allotted time, but we are, I would say, still okay. So, thank you for your presentation. Is there any questions from the audience? I don't see anything yet. So I will ask you a question if you don't mind.
Yes.
Well, and in your opinion, you discussed a bit in the very last slide that you might try to understand how you can exploit some knowledge from experience. So in your opinion, your approach would take more advantage from, an increase parallelization or some learning strategy? Which one would you tackle first if you
definitely learning. Parallelism, it's helping, but the performance are really sensible to the parameters, in the sense that the width of the MDD that you use and the number of the MDD that you use make really difference. For example, on the GPU, I generally use MDD of width 5, but I make 10,000 of them in parallel. So I don't think that parallelism is, I mean, I exploit enough parallelism, but learning definitely will help in guide the search.
So do you already have any idea about
I
how?
I was thinking about have some statistical
Hmm.
data collection about how often an assignment lead to a solution and how often that assignment lead a good solution.
So it's more about the I would say instance driven, this kind of some kind of instance driven learning.
Yeah, what I would like to do is learning within the solving, not among the instances, but just
Mhm.
have the search that as far as it proceed, it get better and better.
I see. Thank you.